Okay, we should now be recording. All right, so welcome everyone to another QUICS research seminar. Today we're going to be hearing from Iordanis Kerenidis from CNRS and also from QCware. And he's going to be talking to us about quantum machine learning prospects and challenges.
Great. Thanks, Matt. I'm really happy to give the seminar. Hopefully in the future I will be able to give a seminar in Maryland, but for now this is, as good as it gets. So I'm really happy to be here. I will just start sharing my screen so you can see my slides. Okay, so in principle you can see my slides. So let's see. Yes, so I decided to give a talk about quantum machine learning and give you a little bit different flavors of what we are trying to do, and then just leave a lot of some time at the end for discussion. So I won't go through too many technical details, but I want to give you a flavor of basically what we have been doing in the last year or so. Okay, so I guess the first question that I'm always asked is that why should we care about quantum machine learning? I think some of you are working on it, so you should, you have already answered this question for yourself, which is good. But here is kind of why I think that quantum machine learning is an interesting area to look at, right? So I think the first reason is that we know that if we had very good quantum computers, like as big as we want, and having access to quantum data and all this kind of stuff, then we can offer provable theoretical speedups, right? Or at least for certain cases, right? So there are quite a few algorithms that have been, proposed in the last 3-4 years, where one can kind of rigorously analyze the running time of these algorithms. And then usually, the running time of these algorithms have many more parameters than in the classical case. But you can see that for at least certain regimes of parameters and certain data sets, one could expect to provide some speedup with respect to classical algorithms. Okay, so that's a good starting point, because it's not always the case that if I give you a quantum computer, you can provide a speed up. So at least we know of some speed ups of that form, right? And what I want to discuss a little bit more today is whether we have to actually wait until we have these full-on fault-tolerant quantum computers, or what can we do while waiting for this, big fault-tolerant quantum computers, right? So I'm not going to claim that we can have quantum machine learning applications with the computers that we have today, because they're pretty bad, and not necessarily maybe tomorrow. But the question that I have been trying to ask all this time is that how much can we kind of bring all these algorithms closer to where we are today? Okay. So do we have to wait 20 years or 10 years? So there's a big difference between 10 years and 20 years, let's say, right? So the main thing that the main way that we're trying to do that is by looking at the quantum algorithms that we have for all these applications and figure out, can we somehow reduce the resources that we need, right? And it will be great if we could reduce the resources and at the same time keep exactly the same performance or the same impact. Or sometimes we have to say that, okay, we need to start getting not the entire speed up that we would hope for if we had these big computers, but at least some speed up that starts from smaller computers and stuff like that, right? Okay, the other reason that I think quantum machine learning is interesting for quantum computers is that because it's not really an exact science, right? So, many of these applications that we have, you want to do things like, all right, you have, cats and dogs, and you want to classify cats and dogs. Already, when you're training your neural networks or when you're using different types of classification techniques, you have to deal with the fact that your data is already very noisy, right? If you look at pictures of cats on the internet, then it's not a clear cat and nothing else. There are many other stuff happening in these things. And even if you add a little bit of noise to the images, the machine learning algorithm should still be able to recognize that it's a cat, right? So somehow these algorithms that we have in machine learning, they are kind of robust in noise, right? And this is noise both on the inputs, but also many times we actually artificially inject noise to the computations, right? And there are quite a few reasons why we want to do that. One of them is for privacy. So when people start discussing about privacy and machine learning, one of the kind of canonical techniques that people use is to actually add noise while they're training the neural networks, or add noise while they're estimating distances, because this way, when you have your model, you cannot so easily go back to your data, right? So when I want to use some data which is private, and I want to create a model and show the model to the world so that they can use it, somehow in order to keep the privacy of the data, many times I add noise while I'm training or while I'm creating this model. Right? And why is noise good? Because quantum computers are kind of noisy. So here we don't need to artificially inject noise to the quantum computations. We just need to get your favorite quantum computer from whatever company you want. It has as much noise as you want, and mostly much more, but that's the best we can do. Okay. And the other reason is that we have some quite powerful quantum tools, right? And I say here that they're powerful in one way and very subtle on the other way. And this is kind of everything that has to do with what we call linear algebra, right? So things that have to do with, inverting matrices or multiplying matrices or projecting into eigenspaces and sub-eigenspaces. So these are kind of things that we kind of know how to do quantumly and quite well, quite efficiently, right? This goes back all the way to phase estimation, right? To kind of some fundamental things in quantum computing. But then there has been a lot of recent work on how to solve linear systems and how to do Hamiltonian simulation and all these kind of techniques. They give you some, as I said, powerful yet very subtle tools on how to do linear algebra, right? And the reason that this is important for machine learning is because in the end, machine learning is mostly linear algebra. Like if you can multiply matrices together, or if you can solve linear systems, then you can do many, many different things in machine learning. So there's another final reason that I have started trying to understand a little bit more, and I don't have an answer. It almost feels like a cop-out, which is that maybe if we cannot provide better efficiency or better accuracy, there are other things that we could hope to provide, right, using quantum machine learning. And these are things like interpretability and trust on one hand, and energy savings on the other. So what do I mean by interpretability? So this is something that is becoming more and more important in classical AI and classical machine learning, which is that in many cases, even if you can use a neural network and kind of get some very good accuracy results for classification or things like that, it's very difficult to be able to explain what you are doing in the algorithm, right? So the reason why you say this is a cat and this is a dog is because the weights of your neural network are trained to be 0.3 and 0.5, but it doesn't give you an interpretable reason why the algorithm chose that this is a cat and this is a dog. And this may not be very interesting at all when it comes to discussing cats and dogs, but this is quite important in applications, for example, in healthcare and machine learning, where you want to see if you should do an exam to a patient or not, and you use a machine learning algorithm to cluster your patient according to some group of patients that should have the test or they shouldn't have the test. And then going to the patient and saying, my neural network told me that I should not do an exam or I should not give you the surgery, is not something which is, even by law, it's not something which is enough, right? So there you need some sort of what we call more interpretable methods, and these are the more heavy linear algebra methods, right? So these are things that you kind of probably already heard of, things like decision trees or even support vector machines, nearest neighbors. These are kind of techniques that you can try to explain a little bit more why you're taking this decision, and they could be useful even if somehow they don't give you as good results as a neural network. Okay, so here is a couple of papers that I'm not going to talk about all of them, but I wanted I will hint on some of them, but it's not very important. Okay, so I wanted to just make a small distinction, right? So what I said is that, here is what we want, right? How do you get to these applications, right? Because especially with machine learning, it kind of doesn't make sense to have something that theoretically works if it doesn't work in practice, right? So somehow machine learning is something that has to work in practice, like you have to do things with it, right? So we want to be able to have good performance, right? And, have algorithms that actually achieve something, and we would like to have as less hardware requirements as possible, right? So one thing that, one way of trying to get to that target is to say, okay, this is the hardware that I have today. So I'm just going to use the hardware that I have today and try to find the best thing that this hardware can give me, right? And this comes down to using a bunch of different heuristics. So it's the same as, in chemistry, you use the VQE type algorithms, and for optimization, you have these QAOA type algorithms. So for machine learning, you can also have this sort of quantum neural network techniques where you define your neural network as some sort of quantum circuits with a bunch of parameters, and you try to train these parameters so that your quantum circuit will give you what you want at the end, right? Classify cats and dogs, right? So this is a very interesting thing to look at. It's a little difficult to be able to benchmark these techniques. And the main reason for that is that when you want to benchmark a neural network, what you do is that you take some data sets, you run them, and you see what results you get, right? But for that, for having meaningful results, you need to run a neural network of some size, right? So it could be 1 million, or actually it could be 1,000 or 10,000 nodes of this neural network that you need in order to say something interesting in real world data sets. And quantumly, we cannot do that, because on one hand, we cannot have a 1,000 qubit neural network right now. So we cannot do them in practice somehow. And we cannot simulate very easily 1,000 qubit circuits either, right? So kind of the only information that we have, or evidence that these things will work, is examples with very small number of qubits. It would be 4 or 8 or 16 if we are lucky, or something. And it's not very clear how to generalize what you get for something so small into something much bigger. It's great that it works in these small examples. If it wouldn't work even for these examples, then you shouldn't be expecting that it continues to work, right? But I'm just saying that as the hardware improves, then we will get better ways of figuring out what type of heuristics we are able to use, because heuristics, you have to try the heuristics out and see if they work or not. So what I will discuss a little bit more is kind of going the other way around, which is that we have these quantum machine learning algorithms, as we said in the beginning, that if I give you everything you need as resources, then you can mathematically prove that you can get some speed up in some cases, right? But the hardware requirements is kind of very far in the future. And the main idea is that how can we kind of push these things towards something that both has some decent performance and decent speed up, and also has hardware requirement that may not be what we have today, but it's getting more realistic, let's say, right? All right. Let's go into a little bit more detail on the QML applications, right? So I want to define a couple of bricks of the things that we will going to use in order to look a little bit more at the machine learning applications. And the first one is what we call a distance estimation. So this is something that everyone kind of learns quite early in the quantum algorithms course, which is that if I give you two quantum states, it's not so difficult to estimate the inner product between the states or the distance between the states, right? So there is the swap test that one can do. And here is another kind of simple way to do it. And I will tell you why it's a little different than the swap test. So here I'm just saying something very simple. Imagine that you know how to construct two quantum states, X and Y, and you want to find something about the distance between X and Y. So think of X and Y as your data points, right? So for now, let's say that you know how to construct this X and Y. So you can, construct X and Y with a control qubit. On 0, you construct X. On 1, you construct Y. And if you do a Hadamard on the first qubit and you measure, then you get exactly something which is proportional to the square Euclidean distance between the two, right? The small difference with the swap test is the swap test gives you something which is proportional to the square of the inner product and not the inner product itself, which means that if for some reason your data set is such that the inner products can go anywhere from minus to plus, then with the swap test, you will not get necessarily something proportional to the distance because you're only estimating the square of the inner product. But as you see, it's very simple to see that how you can deal with this, and there are many different ways of actually doing this, right? So I guess one way that you can start estimating this distance is by just creating the quantum states and then start sampling ones and figuring out how many ones you get. But as we know, you can do something better, which is that you can do some sort of amplitude estimation to estimate what is this probability of the outcome 1, and you can do it coherently as well, and you can have some sort of distance estimation procedure that runs in 1/epsilon steps and provides this estimate to the Euclidean distance up to an epsilon error, right? Okay, so in high level, what I'm saying here is that if mapping your data points to quantum states is efficient, then the distance estimation is also very efficient, right? So it takes log n time to actually do this operation, and you need 1/epsilon steps to estimate the thing. So in something like log n/epsilon time, you can get an epsilon estimate of the distance, right? This is because I'm not counting how difficult it is to create these quantum states, because we say that for now, let's assume that it's efficient to do that. Okay. Okay. So once we have this distance estimation, we can start doing simple things with machine learning, right? So what is the simplest kind of problem in machine learning? Well, you want to classify things, right? And there are many different ways of classifying things. Like the more traditional ways for classifying things is the things that are basically called similarity learning or learning based on distances, right? So these are algorithms like k-nearest neighbors, nearest centroids, and these basically look at how far or how close your data points are and kind of group them together. Right? This is the main idea. Now, before you do this classification, usually what you have to do if you want to use these algorithms is not to look at your raw data, but you take your data, you project them into a different space, because in this new space, your cats are all together and your dogs are all together, right? So finding this space is not always trivial, but many times what we do is we do some sort of techniques to map from one space to the other, that sometimes they're called dimensionality reduction. And again, this kind of dimensionality reductions many times have to do with linear algebra. So for example, you do a PCA, like a principal component analysis, and you keep the top eigenspectrum of your data matrices, okay? Then we can use support vector machines. This is actually a very efficient, actually very accurate way of doing classification. It's not so efficient when you really want to do the the kind of real support vector machines, which is this L1 distance support vector machine, because this is kind of a problem which is, let's say, somewhere between a LP and an SDP, right? So somehow it's not so easy if your matrices start getting bigger and bigger, but this is one way that people actually in practice do classification, especially when you don't have too much data and you cannot train your neural networks very efficiently. And the fourth one is using neural networks, right? So this is kind of, this fully connected neural networks, or the convolutional neural networks. And the quantum analog of this is kind of what we call variational circuits, or parametrized quantum circuits, or quantum neural networks. So, they go with different type of names. Okay, so here is an example of the most kind of trivial way of doing classification, right? So the nearest centroid is the simplest thing that I could find, which says what? So imagine you have data and you have what we call some training data. So you have data with their labels. So you have a bunch of photos that are named cats and a bunch of photos that are named dogs, right? So now the hope is that you find a way that when a new image comes, that you can say if it is a cat or a dog. Okay, so what do? The first thing is that you feed your model, and feeding the model is very easy. You kind of compute your average cat and your average dog. So what does this mean? If you take all these images and you look at them as points in space, then you find the centroid of all the points that are labeled cats, right? This is the barycenter of all the points in the cluster, right? And then when you want to predict a label for some new image, some new data point, then you just compute the distances between the new point and each one of the centroids. You find the closest one, and you assign the label of the closest one, right? So this is kind of the classification 101. And this is, it's quite simple now that you can find the most trivial kind of quantum algorithm that you can think of, which is, okay, go to the point where it says compute the distance classically between the points and the centroids, and try to do it quantumly, right? So this is kind of the least quantum thing you can put into this algorithm. You keep everything else classical, and you just inject this quantum step there. You can start doing more elaborate and more fully quantum things if you want, but I will discuss a little bit more later. But this is kind of the least, let's say, quantum hybrid, whatever you want to call it, classical quantum way of classifying, right? So the question is, okay, how well can you start doing these things? So again, as I said, it's not very trivial to figure out whether this will work in practice, right? In theory, you can say exactly how many qubits you need, what kind of, what do you expect from these distances, and theoretically you can do a lot of things, but the question is, does it work in practice or not, right? So to see if something works in practice, you kind of have to make it run. So in order to make it run, you kind of need to write some software, which is not what I'm very good at, but it's kind of simple. Obviously for this is quite simple because it's a very simple algorithm, but it's kind of simple to follow kind of the same steps as the classical algorithm. And at the particular points when you want to use your quantum procedure instead of the classical procedure, you just interject this new quantum way of doing things, right? So this is just a very small example to show you that the same way that you can use scikit-learn, this is kind of one of the most popular classical machine learning things. And you can use your nearest centroid, you give it your training data and the labels, it fits the model, and then it predicts the model. Then you can kind of try to do a similar thing quantumly. And what we get, whoops, sorry. I think the mouse actually moves things around, is what you get is results which are kind of good. Theoretically, you get exactly very similar results to the classical one. And we kind of started to try to really implement these things, right? And we work with one of the, let me call them one of the good hardware partners that you should be quite familiar with because they're not very far from where you are. And the question is, what is the best thing we can do with their machine, right? So they used to have around 10 or 11 qubits. Now they have a little bit more. The question is how big of a data set and how big of, of dimensionality of data can we fit in a way that actually you get decent accuracy, even if you run it on the quantum machine, right? So we kind of produce some synthetic data. We looked at the MNIST data set, and kind of what we find is that for generic, synthetic data, the quantum algorithm works pretty well, in the sense that, okay, for 4-dimensional data, you get exactly the same results as classically. For 8-dimensional data, I think we got 1 error more than what the classical thing does in some sort of 50 elements or something. So these numbers are not so important because, again, these are quite small data sets. But the idea is that, you can see these things starting to work somehow, right? And of course, it's not, in some sense, it's not at the level where anything interesting can come out of this, right? Because these are data points with 8 dimensions, right? So it's still, we have pre-processed the data sets to be very, very small. But what you get from that is that, on one hand, you can start testing these algorithms already. And on the other hand, theoretically, you know very well how they will scale when you grow, right? You know very well how to analyze the running time of these things when they, when you go from 8 qubits to 16 or from 8 dimensions to more and more, right? So the reason I think these are quite interesting is again, because here we're not doing heuristics with, with a bunch of qubits and see how it goes and kind of interpolating of how this should work when it scales. But here we kind of know how the scaling goes. We know exactly how these algorithms work. And we know that we can get some small speed up when the computers will be big enough. And you start running them and seeing whether, mostly whether your quantum computer is good enough or not. So to me, this is kind of a very nice way of benchmarking quantum hardware, because this is something that we would like to do, like classify points, right, in the future. So it's a very different thing to talk about the fidelity of the gates, but to me, it's a much more interesting thing to say, how well can you classify 8-dimensional data with your quantum hardware, right? So that's why I think these more algorithmic benchmarks for quantum hardware it's quite interesting, and we should be getting more and more of this out there. Okay, so I talked a little bit about dimensionality reduction. So these are kind of all these techniques, this like principal component analysis, linear discriminants, low feature analysis, all of these things in some sense they have been quantized, right? And the reason they have been quantized because they all kind of have to do with estimating eigenvalues and eigenvectors of matrices, right? So doing all these kind of techniques from Hamiltonian simulation, the singular value transformations and all these type of techniques, you can do things like project on subspaces of your eigenspace, depending on whether you want to keep the high eigenvalues or the low eigenvalues sometimes, or something that depends on the eigenvalues, basically, right? Now, the reason I find this interesting is because classically, this is not a very easy thing to do, in the sense that usually you, like in practice, you do spend kind of cubic time on the dimension, like if you have an n by n matrix, to do something like SVD or PCA, right? So this kind of grows quite fast, the running time. And this is one of the areas where, quantum computers can do something interesting, right? Meaning that you can kind of try to project your quantum data from your initial space into this new quantum space, which is this kind of principal component space or something, right? The other good thing why I think this is very interesting is because one of the difficulties for this type of linear algebra things is the fact that your output is not your classical solution, but it's it's a quantum state that encodes your classical solution, right? So this is where you say, okay, but if you want to extract your classical solution, then you have to start doing tomography and figuring out what your state is, right? But here, this is not what you want to do, because what you want to do after you project your vectors there is to do some quantum classifier afterwards. And what we said is that the way we want to do this quantum classifier is by creating the quantum states that correspond to the data points. But this is exactly the outcome of this quantum dimensionality reduction procedure. So if you start with your data, if you do this quantum procedure, you end up with a quantum vector that corresponds to the projection of this data into your space. You don't need to figure out what is this projection. You just need to put it into your quantum classifier afterwards as a quantum state in order to see if it is, as we said, a cat or a dog, right? So, and the good news here is that even if it takes you some time to prepare these quantum states from the classical data, here we're talking about a procedure that takes kind of cubic time on the input sides. So in the worst case, even if you spend linear time to go from your classical vector to your quantum state, if you can do fast this linear algebra procedure, then still you get a much faster way of getting this projected data into the right space than with a classical computer, right? The main problem is that this PCA and all these kind of linear systems is not something that can be done very, nisky, as as we say. So, and I think this is the main kind of open question here, that how do you what is let's say, what is the least amount of resources that you would need in order to do some interesting heavy linear algebra? And I call heavy linear algebra not multiplying vectors, which is like what you do in matrix multiplications, because we saw how to estimate linear products. But more heavy linear algebra, meaning like how do you invert a matrix, or how do you do SVDs and things like that. Okay. Yeah, so kind of this takes me to the quantum linear algebra. We said that, we know how to do efficiently in certain cases this singular value estimation. This has been adapted to what is called singular value transformation, which has a much better dependence on the error. You see this log 1 over epsilon instead of the 1 over epsilon. This is kind of using this notion of block encodings and techniques that were developed for Hamiltonian simulation. And based on that, you can do all these kind of linear systems and linear algebra stuff, right? But again, doing this kind of techniques, the singular value transformation, is not a simple thing, in the sense that you still need a quite deep quantum circuit. And yeah, it's quite interesting question to figure out, can you do something even like phase estimation without needing the full-on quantum circuit that we know about phase estimation, right? So some of these questions, for example, when you look at amplitude estimation, there have been a recent series of works on trying to reduce a little bit the resources that one needs for amplitude estimation. So there are these works by Suzuki et al. And Scott that kind of have removed the need to do the quantum Fourier transform at the end of the amplitude estimation circuit. It doesn't help much, because this is kind of not the bottleneck of the thing, but these are very interesting questions on how can you get niskier versions of this kind of basic quantum tools like amplitude amplification, amplitude estimation, phase estimation, and so forth. All right. So yeah, I don't want to talk about the recommendation systems again, but you can ask me if you want. It's a old kind of debate. So I wanted to give you a couple of more slides on some of the things that we have been doing recently on trying to remove some of the bottlenecks that we said about machine learning, right? So one of them was, how do we load classical data into quantum states, okay? So why do we need to do that? Because data is classical, and Of course, one can come up with ways that quantum data will be interesting, and I'm sure there will be cases where quantum data will be interesting. But still, I think most of the data around us is classical, and somehow if we want to do machine learning with an impact, we need to be able to deal with classical data, right? So the main question is, how can we kind of load this data into a quantum state? And what we have been developing is try to understand, okay, what's the best way of doing this, right? So let me try to formalize a little bit the question. So I give you an n-dimensional classical vector. Let's say it's a unit vector, right? So there are n-1 real values, which are the coordinates of this vector. And what I would like is to figure out a way to create the state that corresponds to this let's say, unit classical vector as fast as possible, right? So the first thing to see is that you do have n-1 degrees of freedom there, right? Because I can give you any, let's say, any possible numbers that make a unit vector. So somehow you need, the size of your circuit to incorporate this n-1 real parameter somehow, right? So here I'm talking about really loading the classical data, not something that could resemble the classical data or could be a kind of compressed version of the classical data or things like that. So let's say we did all the pre-processing, we have something that we really want to load, okay? So as I said, we do need to use n-1 kind of parameters in this quantum circuit. And kind of what we figured out is how to use exactly n-1 gates for this quantum circuit, right? And the more interesting thing is that you can kind of play around with the resources that you have, right? So what are the resources in a quantum circuit? It's kind of the number of qubits and the depth of the circuit, right? It's also the number of gates, but let's say we fix the number of gates to be n-1, right? So what I show you here somehow, okay, maybe it's easier to see it here. So there are many different ways of trying to do that. So what we can do is that this is actually very simple, right? It kind of was there already. So you can use n qubits to load an n-dimensional classical vector with a quantum circuit that has exactly log n depth. Okay, you use n-1 2-qubit gates. These are parameterized gates, and these n-1 parameters depend on the classical data. And this kind of gives you some sort of unary encoding, in the sense that you do have to use n qubits for n dimensions, right? But what you get is, for a real classical vector, not just 0 or 1 vector, you get exactly the quantum state that corresponds to this classical vector, right? And I guess the more interesting thing is that you can trade off this number of qubits and depth, right? So for example, you can, sorry, I lost my, you can use square root n qubits and square root n depth in order to do the same thing, right? So somehow, to me, it's not very clear what will be happening in the future, right? Like, is it easier to have 1,000 qubits and a depth 10 circuit, or is it easier to have 100 qubits and 100 depth circuit, right? So this kind of depends on your errors and what's happening. But somehow, in the simplest case, if you only care about kind of squeezing the circuits and making them as shallow as possible, then we can kind of take it all the way to log n, as long as you use n qubits. And kind of the assumption here is that if you have a log n depth quantum circuit, the time it takes to actually go through the circuit is order log n, right? So this is a circuit of size n. It has log n depth, and we're kind of assuming somehow that you can apply gates on different qubits at the same time, right? And I think Matt was with me in a meeting some time ago, and we were discussing it with experimentalists, and we were saying, is this a fine assumption to make? And what we got from them was, yes, it is reasonable to think that this is possible. I'm not saying that, it will be possible for every technology. For example, for photonic, it's trivial to see that it should be possible. For other ones, you have to deal with it. Okay, so maybe I have a couple more minutes. So what I want to just say that, okay, so we kind of loaded these gates, and I'm sorry I didn't give you much more details about this, but there will be a paper out in a couple of weeks, or maybe a month, let's say. So all the details about these data loaders will be there, right? But somehow the important thing about these data loaders is not the data loader itself, it's what can you do with them, right? So what we wanted to do is this distance estimation stuff without having to do the swaps, without having to do many kind of more difficult quantum operations. And basically what we can show is that doing distance estimation is the same as kind of loading the data. It's kind of how it was in the more circuit-based the example that I gave you in the beginning, where you could do whatever gates you wanted, and then you could see that once you know how to create the data, it's very simple to do this, to estimate the distance, right? So somehow, if I have two 16-dimensional data, the good thing is that I don't need the double number of qubits. I don't need 32 qubits now, but I can actually do it with 17 qubits. So this is just the dimension plus 1 qubits if I use the log depth circuit. And this is also a 2 log n quantum circuit that will be able to do that. We can use this, distance estimation is the same as we said as inner products. That's what we're estimating. So inner product is just, vector-vector multiplication. So you can use these things to do matrix vector multiplication, obviously, and things like that. So again, we can kind of have log depth quantum circuits for doing matrix vector multiplications. It's pretty simple. It kind of follows. And this also kind of gives us an idea on defining some sort of quantum neural networks that we can kind of try to be able to prove things a little bit better than just running them, but somehow try to be able to theoretically say something interesting about the neural network. So there are many different neural networks, right? To be honest, I don't know all of them, and there are many more. And I think there's some very interesting work there. So the main thing that we try to do, this is some earlier work, which was keep the neural network classical and try to speed up the training. And why is that? Because the training is linear algebra, right? So this is kind of one way of trying to deal with this. Still, it's not a very NISQ way to do things. So the main challenge for us was kind of how do we define quantum neural networks that we can start using, and at the same time be able to say something interesting theoretically about them, right? So what we kind of figured out a little bit, and this is kind of work in progress, but I wanted to put it out there, is how to define some sort of neural network architecture that maybe not as NISQ as the constant depth neural nets that people use in practice, but somehow have a decent kind of easy circuit which is defined, and be able to show something of the following form, that these quantum circuits are at least as accurate as the classical one. So if your classical equivalent one was not working, then this is not going to work, but you cannot really be worse than what you would expect from a classical neural network with a similar topology, right? And kind of the circuits that we use in between are kind of not totally NISQ, but kind of, n qubits. If it is an n by k, if it is a n by k layer, then it's n qubit and k depth circuits somehow. Okay, so I will stop here. I'm not going to say much about clustering. We did some sort of Q-means, but then we had to extend it to expectation maximization and to spectral clustering. So these are kind of interesting. And again, they're just using the same toolboxes, the same linear algebra at the bottom, because as we said, most of machine learning is linear algebra. And reinforcement learning, this is my last slide. It's kind of interesting to me for the following reason, right? So what you do in reinforcement learning is that you try to get a strategy of how to play a game or how to move around the room or things like that. And the main kind of framework on how to do reinforcement learning is that you start with a random strategy that kind of loses all the time, but little by little you try to update and to improve your strategy, right? And the way that you improve your strategies happens in two steps. The first one is you try to find a way to estimate or evaluate this function, which is called the Q function, this value function, right? And there are different ways of trying to do that. One way is by solving a linear system, right? And the other is by using a neural network that you train in order to give you this function Q. And then from this function Q, you can update your policy, your strategy, right? The reason I'm kind of interested in this is that this is an area where you don't have this main problem of the supervised case where there is all these gigabytes of data and how do you load this into the quantum system little by little and all these things. So the data here is kind of produced while you're trying to learn how to play the game, right? So in the beginning, there's no data. And then little by little, your data is that, okay, I used this strategy and I lost the game. Or I explored a little bit some neighborhood around me, and this is what I know. So somehow this data is not at the same level of unstructured as like random images from the internet, but it's kind of, you have functions that kind of compute this data. Like you are in a state, you take a move, you know what your next state is. You go up, down, left or right somehow. So these are data that are kind of constructible by short classical circuits, and hopefully, and also by short quantum circuits. So there's not this notion of input. Also, if you want to do this linear system, this is a well-conditioned case because you have this gamma factor here, which is less than 1. And the guarantees that you need in order to solve this linear system as the weakest possible that you could imagine, which is that you don't want even L2 guarantees on the solution, but L infinity guarantees is what you need in order to prove that this thing works. So even your tomography that you may need to do at the end of this linear system, it will be independent of the size of your circuit because you just need L infinity guarantees. All right, I'm going to skip this, and this is my conclusion. As we said, we have some very powerful quantum tools. The question is, how do we use them in a way that it makes sense and we kind of, solve something. We don't know how to get QML applications right now. It's not very clear how to get them next year or in 2 years either. But somehow there are interesting avenues to look at, right? On the longer term, things that have to do with heavy linear algebra are good candidates, like spectral clustering, classical is n-cube. We did some experiments, and putting all the parameters of the linear algebra in, you get linear in n running time instead of n-cube. So this is a quite interesting speed up that hopefully at some point you can see in practice, right? Reinforcement learning is pretty cool as well. I'm kind of getting into it. I don't know too much about it. Quantum neural networks as well. And the last remark is that ML should work in practice. So I'm happy with quantum theoretical algorithms or quantumly inspired classical theoretical algorithms. If they don't have any chance of working in the real world problems, then they remain some very good theoretical results. But this is not what will, make or break machine learning or quantum machine learning. All right, thank you a lot, and sorry for taking 5 more minutes than I should have.
All right, thanks, Iordanis. And no problem, I think we're okay on time, and I'll take some questions I see. All right, okay, good. You're getting applause. That's what that is, and And I know we have some questions in the chat, so I think we have two, and I'll go through them. I'll go through them in order. And Eddie or Ikai, when I get to your question, feel free to unmute also and state your question. So we have one question from Eddie, and I believe, if I remember correctly, this came up on there's some plots on the slide right before the quantum dimension reduction slide. Eddie is asking, why is the quantum result different? And is that from noise on a real physical device?
So yes. So why are the quantum results different? So the quantum results are different even if you have your full-on quantum computer, in the sense that what you are doing is not, if you're doing distance estimation quantumly, then you are approximating the distances, right? What you say is that in time 1 over epsilon, I go epsilon close to my distance, right? So you add this noise on the device, even if your quantum computer is supposed to run perfectly, right? Now, when you are actually trying to implement this, then there is extra noise on how you estimate this distance, because your quantum computer may also be noisy, right? The corresponding classical algorithm that is on scikit, for example, is something that computes the inner products exactly, right? You could also have classical approximate algorithms, right? So instead of computing the entire inner product, you can try to do some sort of L2 sampling and estimate the classical inner products. But these kind of things don't work as well as the usual classical things, right? So the difference comes from noise that is inherent in the quantum procedures that estimate quantities and not perfectly calculate the quantities. And there will be much more noise that comes from the implementation. I hope this was the question.
You say the classical routine calculates it perfectly, but this is also with floating point arithmetic, right?
Sure. So let's say that.
So you just, if you set the epsilon to the same precision,
of
like,
course,
32 bits, then,
yes,
it should be the same.
It should be the same, and it will be the same. It's just that the number of samples you need to take is 10 to the 2 to the 32. And, if you want the 2 to the minus 32, estimation, right? So this is not what we want to do. What we want to do is to pick epsilon to be 10 to the minus 2 or 10 to the minus 3. And the good news is that if you want to classify points, right, if you just fudge the points a little bit, the classification should still work, right? So this is why this is good, in the sense that we don't need epsilon that goes up to floating point or anything like that. Like, I think epsilons 10 to the minus 2 already give you good results for the MNIST data set, right? So these things are kind of robust. You can see it, you have the points here, the points there. If you, put some noise on them, you can still see the clusters somehow.
Yeah. All right. Thanks.
Okay, great. And so the next question is from Ikai, and he is asking how much classical computation is required to run the quantum data loaders, or if you're doing classical side computation. And he also asks, if you're willing to do more classical computation, could you then reduce the number of qubits or the number of quantum gates?
Yeah, very good. Okay, so the time that you need in order to be able to start using the quantum circuits, right? You have to read your classical data once, and you spend logarithmic time on each coordinate, let's say. So you spend like linear, or let's say n log n time on the classical data, right? Once you read this thing once, then what you get is that you get all the parameters that you need to store into the gates of the circuit, right? And then when you run the quantum circuit, it has log depth, right? So this is not good if you just want to do one thing with your data point, right? So if you just have one inner product that you want to do between one data point and another point, then you have to read the points, right, before creating the quantum circuits. So then your time you will spend is the same as you will spend classically, or even more, right? when this starts becoming more interesting is in cases where the same data sets is used many, many times, right? Because then you only do the pre-processing once to find these parameters. And then every time you want to use the data, you only spend the log time, right? So for example, to be more precise, if you have a matrix multiplication, right? So you want to do all these inner products. You need to read both matrices once, right? So this takes n squared time, right? And then you have to create your quantum circuits, find the parameters, which is again n squared time. But then for each one of these inner products, right, you can start getting information in log n time. So you don't spend, let's say, n cube time if you are doing the kind of naive matrix multiplication, but you spend linear time once to read the data and prepare your circuits. And then in log time, you can start getting information about the linear product, right? So this is only good if you have to use your data many times and not just once, because in any case, you have to read your data, okay? So this is the first question. The second question was, can I do classical pre-processing to reduce what I need in the quantum circuit? So yes and no. So no, in the sense that if you have no structure in your data, meaning that if you just want to load like random n-bit strings, right? Then you no matter, somehow even information theoretically, you need these n-1 parameters, right? So if I tell you that, okay, you just are getting random vectors there, right? Then you need to read them. At the same time, if there is some structure on your input, or if you can compress your input, right? Or, maybe you have too many points, but they are almost the same, and you can kind of take a subset of them and still be fine, right? Or project them all. Maybe you have too many features and you can just do some feature selection, and then this is good enough for you. So all of these things you can do, let's say, before, right? And then when you need to load the data, for us, you spend this much time. But it could be the case that if I give you a matrix of data and I tell you something about the matrix, like there is some structure, or it's lower rank than the full rank matrix, or things like that, that possibly by using more time on figuring out the structure on your data, then you could be able to create shorter circuits, but these circuits would be only for this particular data. So somehow you would have to redo this type of thing for every new data set somehow. Right? So this is kind of the most generic thing that I don't look at the specific data. These kind of circuits work for any data, but if you have some distribution or some structure on your data, maybe you can create specific loaders for the specific data.
I see.
Okay, thanks. And I'll move on quickly because we have one more question. So there's a question from Dao Chen, who says, thanks for the nice talk. What is the quantum speed up you get for reinforcement learning? Or maybe the question should be, do you get a quantum speed up for reinforcement learning?
Yeah. So the thing that we have worked out so far is the first one, where you solve a linear system in order to do the update or the policy update, right? And for that, you get the normal speed up from solving quantumly linear system versus solving classically linear system. To be a little bit more precise, this will depend on many things like the condition number, this parameter, whether it is the sparsity or the Frobenius norm of the matrix, the error that you need in the solution, and all these things. And this is where I try to say that these are all good cases for us, in the sense that your matrix is well conditioned, right? So your condition number could be like 10, because this gamma thing is like 0.01 or something like that. So it could be 10 or 100, but doesn't grow with the dimension. So you have a bounded condition number. the accuracy you want from the solution is an L infinity accuracy. So the extra thing you pay is a 1 over epsilon square, but not dimension over epsilon square. So this is also good if you want the classical solution afterwards. And the third one was, it's, what was the third one? Yes, the third one is how easy it is to actually get quantum access to this memory in order to do your quantum linear system solver. And for that, in principle, for simple games, there's simple functions that, given the element of the matrices, the indices of the matrices, you can compute what is the value of the matrix. So you don't have to store it. You just need to be able to compute some easy functions on the game. But this is not for all games, but for quite a few games, it's easy to get these transition matrices and stuff.
Okay, and Dao Chen says thanks for the answer. And is there a yeah, Xiaodi, go ahead, ask the question.
Hi, Hank. So I have a. Actually, I'm sorry. Maybe I missed some of the talk because I just went to pick up my daughter. So I'm not sure whether you addressed this, but I think this is something I have trouble in my own research. I don't know how to do. So the question is about how we can actually empirically evaluate those proposals. I mean, whatever proposal we have. The sense is the trouble is that sometimes when we say you have some speed up, but like empirically doing that, actually I don't see a way of doing that. The reason is that we don't have the large quantum machine, and then you resort to simulation of those algorithms, and then when you do that, you don't really see speed up in that actual computing time. But you might need to change the measures, or if you don't claim for speed up, then for some other sense when you claim, you still want to say what's its empirical performance, then you might run to other issues. I just don't know what's your comments or thoughts on that.
Yeah, very good. Okay, I try to be fast. So I guess the same question has a very different answer if you're looking more at the algorithms, like the ones solving linear systems or things like that, and a different if you're looking at quantum neural networks or parameterized circuits that you don't have a mathematical understanding of what's happening, but then you have to try it, right? So let me try to reply to both of them. When it comes to the algorithmic ideas and algorithmic ML, right? So we talked about the reinforcement learning. So you say that the quantum time to do this reinforcement learning depends on the time that your quantum linear system solver solves your linear system, okay? So again, so this gives you a theoretical understanding of what the running time is, but the question, as you said, is if I try to run it, even in the fault tolerant case, am I going to see a speed up or am I not going to see a speed up, or how do I know whether it's running fast or not? So the main way that we were trying to answer this question, and I don't think there is a 100% convincing answer, is to kind of try to simulate on an operational level what the quantum algorithm is doing, right? So somehow we are saying that, okay, you solve a linear system, and what I know is that I'm getting an epsilon error on the solution because I'm only sampling these many things, and then the procedure is approximate and so far. So the way we're simulating this thing is to say that, okay, the way I'm simulating is not by running the quantum circuit, right? But let's say I solve the linear system, I get my classical solution, but this is not the solution that my quantum algorithm is getting. I add noise to this vector, and this is what I kind of try to simulate as what the quantum computer, let's say for now, the full quantum computer would give you as a reply, right? So this is one way, and this way you can simulate and see if you get good results or not on the accuracy, right? So do you win the game or do you not win the game, right? The second question is what would be the running time of this? right? And for the running time, the thing we try to do is estimate all the parameters that appear on the quantum running time. So there are many. There are many epsilons, many deltas, many kappas, mu's. There are many parameters. But these parameters are kind of dependent on the data, right? And second, they're dependent on how good approximations do you do. The how good approximations do you have to do, we try out until we get good accuracy. So as I said, I need to make epsilon 10 to the minus 2 if I want to get good results. For the other parameters like kappa and mu and all these things, we actually compute them. We look at our data like a real data set. Or for example, for the SVMs, we picked random SVM instances and we calculated what is the kappa of them, what is the mu, and all of these. And we try to fit, we took 10,000 different instances and we try to fit the quantum running time into something of the form n to some power, right? So for the SVM, for example, if you take all the things into account, you get something like n to the 2.5, even though if you look at the running time, there's nothing that depends on n. It's like there is a log n there in the dimension, but you have these 10 parameters, right? So if you put everything there, you get something n to the 2.5, and the classical one is n to the 2.8, or actually 3.1 or something. So for now, you're not getting a very good speed up, right? So I don't know how to be more precise than that. So I know that it's not as precise because we are not looking at clock speed yet. We are not looking at error correction, things that will make things slower or stuff. But for now, with those algorithms, my first question is, do I think that if I had what I needed as a hardware, that in practice, you could provide something? I don't have the hardware, so I try to operationally simulate what happens, compute every single parameter that appears in the running time, and try to see where I am. Okay?
Yeah, thanks. I think this is very helpful, but I just want to make sure that I have the right understanding. So you're basically saying I want to simulate the perfect machine, and but like assuming the imprecision coming from the algorithm, and
yes.
Yeah, but
so this is for as I said. So when it comes to the big kind of algorithms, then we are dealing with, the first question is, can I get a speed up even if I had a good machine, right?
Okay, so but how about if you have like some iterative algorithm where maybe the quantum output from the previous step to next step generates somehow different distributions that may give you advantage or disadvantage, or we don't know, but those things probably won't really count in your current analysis. So, but you're saying,
yeah. For example, for the SVM, for the support vector machines, it is an iterative algorithm. It's kind of an interior point method, right? So for every step of the algorithm, we had to find the right solution classically, add the noise that we expect from the quantum algorithm, and then use that to define the next linear systems and so forth. And there we had to also look at the convergence. Does it still converge or not at all? How fast, and what is the accuracy at the end, right? So as long as you take these errors to not be too big, the convergence is still okay, your accuracy is okay, and then you have to deal with the running time. And if everything is to your advantage, then you can get the speed up, but not always.
Okay, so in your case, you basically say like each step, you come back to some like ideal classical, there's like standard answer for each step, and you just compare whether the quantum one matches your one. But you say if the quantum one carries error, you just let the error be there, and you just simulate, on top of those errors.
No, mostly what I do is that the solution of the linear system will give you the linear system for the next step, right?
Okay.
So now what I'm saying is that solve classically the linear system, get the new system, but this is not what you use for the next one, because you know that your quantum algorithm will put epsilon error in this solution.
Okay.
So we add artificially noise into this solution, and this defines a noisy linear system that we have to solve next time.
I see.
We solve it classically, we add more noise, then we go to the next one, and so forth.
Okay, so I can see what you're trying to do. So basically for this type of algorithm, your quantum algorithm is it's try to quantize this classical one. So it has like some ideal functionality, but like quantum can give you a speed up. I kind of agree. So what you said is a good way to do some empirical performance evaluation. But my original question was more about when you have algorithm, you don't really know, whether there's standard intermediate steps. So quantum can generate something for you, but generate some randomness for you. You can do analysis, but of course, your analysis may not capture its full power. I mean, either to your advantage or to your disadvantage. Then in that case, do you have any idea how we can empirically evaluate that?
So, all right. So let me say, so for quantum neural networks, for example, right? So that's why I haven't said anything interesting so far on quantum neural networks, because I didn't know how to start analyzing what's happening, right? And the only thing I found on how to do, and we are kind of trying to work on that, is to create quantum neural network architectures that I can prove that at least they can go through all the configurations of the classical one with the same number of nodes and stuff, right? So somehow I'm saying that it shouldn't be worse, because your gradient will at least find something with what the classical one would have found. So this is a theoretical reason why I'm claiming that they shouldn't be worse than the classical ones, but I have no idea how to prove that they could be better, because I cannot run them.
Okay.
So it's a very good question. Yes, we are trying to do empirical science without being able to do experiments. So that's not trivial.
Yeah, before we can do experiments, we probably need some like a methodology to allow us to evaluate their empirical performance. Yeah. But like if you really want to see significant advantage, you need a huge machine. We're not there anytime soon, so we need some like new methodology for the empirical study. So that's basically my question. But I thanks for sharing your thoughts on this.
Sure.
Okay, great. If there, maybe I'll ask one question, and then perhaps we'll wrap up if there aren't any more. I don't see any more questions in the chat right now. So I guess I'm wondering. It seems like a lot of quantum machine learning results, especially these linear algebra type algorithms, have in the case where they're provable results, they have a 1 over epsilon, poly 1 over epsilon time dependence. I think maybe you listed one result that's actually log 1 over epsilon. I can't remember for sure, but it makes me wonder. I don't know if I entirely know the landscape. In these cases, is the classical state of the art also often 1 over epsilon time dependence, or is it log 1 over epsilon? And I guess the big picture question is, are there cases where this could matter? Could we come up with some natural computational problem where it actually makes a difference if your subroutine has 1 over epsilon dependence versus log 1 over epsilon dependence?
Yeah. So for example, the linear system solvers, the more recent and the best linear system solvers, give you a log 1 over epsilon dependence to get the quantum state. Now, usually you get the 1 over epsilon or 1 over epsilon square if you want to extract classical information out of the state, because then tomography is horrible, right? But for example, for the recommendation systems, we didn't want the classical information. We just wanted to sample a big element of this vector. So there we didn't have to pay the 1 over epsilon square on the tomography. in order to do that, though we had to pay it in a different way than somewhere else. So to get to your question, there are things where this epsilon is very important. For example, interior point methods, classical interior point methods, they have log1/epsilon dependence, and that's great, right? The only quantum interior point methods that we know have poly1/epsilon dependence, and that's bad. If you want an epsilon to be 10 to the minus 5, then you have, if you have a 1/epsilon square dependence, you get a 10 to the 10 prefactor. So there's no way to do anything with a 10 to the 10 that doesn't exist in the classical, it is there in the quantum. No matter how faster the other things are, you still have a 10 to the 10, right? So for these cases, I think that the only interesting thing with the quantum would be the cases where you don't need these good accuracies, right? So you don't need 10 to the minus 5. You can do it 10 to the minus 2, right? And there are cases like that. Like estimating distances is one case where you don't need these epsilons to be 10 to the minus 5, right?
Right.
But not always. Like in chemistry, you need epsilon to be even smaller than 10 to the minus 5. That's why it's a difficult thing to do, right? Because the accuracy that you need in your solution is really, really good. For things like machine learning, we are not so accurate anyways, right? So when you're training neural networks, you inject noise. Like basically, if you inject noise, it can, even classically, you get better results than if you don't inject any noise. So epsilon is better than epsilon equals 0 somehow. So that's why it's not that this thing will work for all stuff, right? And we cannot do everything faster. So we gain some, we lose some. Like we lose in the epsilons. Most of the things that we lose in the epsilons. So that's why we should look at cases where the epsilon doesn't need to be very, very tiny, and where the gain that we get from the dimension, for example, going to linear instead of n to the cube, will still allow for some sort of possible speed up. Right.
Okay, thanks. Yeah, I like the case with machine learning and noise. You know, it's like maybe if you're going to add noise anyway.
You do, like you really do.
Yeah, this you know, this epsilon that is an error that is incurred from having a shorter running time can just count as part of the noise. So okay, I like that. All right, I will check. Okay, I don't see any more questions in the chat.
Excellent.
So
thank you very much.
Yeah, and thank you. All right, I guess that concludes the seminar. So thanks to everyone.
Hi everyone, thank you.